Okay, I think now it is streamed on YouTube. So if there are also another person who would like to watch our session today, they can join with us via YouTube. Okay. And also for the participant, I would like to spread our uh, attendance in the middle of session. So please join us till the end. Okay, Bu Prastika, the time is yours.
Okay, thank you so much, Pak Cepi. So let me share the slide first. Now probably you can see my slide already.
Yeah, I can see.
Yep, that's great. Okay, so good afternoon to everyone. Firstly, I'd like to thank you for Pak Cepi, I can call. Thank you very much for the invitations to join this webinar series by UNES, which is called Chemistry and Chemistry Education Webinar Series. So it's really an honor for me to talk in this webinar. So I'm from Universitas Airlangga. Currently, I'm teaching in nanotechnology engineering study program, which is in the Department of Engineering. It's a new faculty, which called Faculty of Advanced Technology and Multidiscipline in Universitas Airlangga. So just built in 2020. We have our first students. So mostly our work in here is based on the nanomaterial for many kinds of applications. So at this time, I'd like to talk about the electrochemical sensor applications since it's correlated with my work in here. Okay, so hopefully it can give you a new knowledge or a new point of view regarding how we use the nanomaterial for electrochemical sensor. Okay, so let me go to the next slide. So Universitas Airlangga is located in Surabaya. As you may know, maybe the logo is shark and crocodile. If you ever come to Surabaya, you can find so many types of culinary and you can enjoy in here. So very welcome. If you come to Surabaya, you can come also to our new faculty. So this is our new building, nano building, which is called. And there is a 5 study program in here, and one is us. It's a nanotechnology engineering study program. So it's very new. We have just graduated our students this year. So just we established about 4 years in here. So I joined Universitas Airlangga from 2019 after I finished my PhD. So basically the work that I will present in here is I did along this year in 4 years during my stay in Universitas Airlangga. Okay, so before we are talking about the nanomaterials and its applications, I'd like to maybe tell you about the nanomaterials. So this is what we are studying here in our study program. So as you know, the nanomaterials, it's a very, very small material, right? If you see in here, the tennis ball, about this size, but the nanomaterials is about this size. The DNA, the protein, glucose, the micelle, liposome, and so on. The virus itself is in nano size material. So we cannot see the nanomaterial size, right? As you know, this person, the Richard Feynman, is the one who introduced the nanomaterials into the world in 1959 at the conference. He talked about there is plenty of room at the bottom. At that time, at the annual meeting of the American Physical Society in Caltech. At the time, he talked about this statement. I don't know how to do this on a small scale in a practical way, but I do know that computing machines are very large. They fill rooms because at that time, the computer size is maybe the size of the room. So it's really big. But now maybe you can bring your own laptop, you can bring your own handphone at your home anywhere, right? So at the time, Professor Feynman said that why cannot we make them very small? Like make them very little wires, little elements, or by little, I mean a little. So at that time, the beginning of the nanotechnology era. So many researchers around the world start to studying about what is this nanomaterial. And the word nanotechnology at the time, we don't know. So there was not a nanotechnology word in the world. So nobody knows. They always say that's a little material, not a nanomaterial. So from the year about 70, maybe, if I'm not mistaken, the researcher from Japan introduced the nanotechnology word at that time. So until now, we understand the nanomaterials. Okay, so if we see from here, the physics, the biology, the chemistry from the year in 1960, all are still studying the complex chemistry, like the macro material until the micro material. But now, for today, there are many devices, for example, electronic devices, photonic devices, as well as sensors, biochips, all are nano devices. Nano devices contains of nanomaterials, of course. So in the next year or in the future, there are many integrations of a biological principle, physical laws, chemical properties, and etc. So there are many applications of nanotechnology. That's why it's emerging technology actually in the world. For example, outside Indonesia, the nanotechnology is already developed. But now in Indonesia, we are still developing, the nanotechnology era. We are waiting where it can bloom in Indonesia. So hopefully in the maybe next 5 years, next 10 years, these nanomaterials, everybody in Indonesia will know about nanomaterials. Okay. Even if we use it in daily life, for example, the silver nanoparticle we already use in the soap, in the socks, but they don't know that this is a nanomaterials. They just feel it, but they don't know the nanomaterials itself. So they use handphone, they use laptop, but most of the people don't know about the concept of nanotechnology itself. So hopefully now your generations, your students in these generations, hopefully we know about this nanomaterials, nanoscience, nanotechnology, and in the future, it become the knowledge that everyone know in Indonesia. Okay. So the second one, because we use this nanomaterial for electrochemical sensor, so I hope you can understand also the concept of the electrochemical sensor. The first one, in sensor, we have the recognitions and transducer and analyzer, and also a signal processing. That is general concept of a sensor. But in this time, we specifically will talk about the electrochemical sensor. Okay, in electrochemical sensor, the first one, we need to have the biorecognitions or the recognition as in general. For example, if we have nanomaterials or any materials that can recognize the analytes, it means the recognition elements. It can be bio or non-bio. Okay, if it's bio, it means we use the enzyme, nucleic acid, antibody, microorganism, and so on. If it's non-bio, then we can use any types of nanomaterials and material or any type of materials that can recognize our analytes. And then the second one, we have a transducer. In transducer, maybe you already know from Pak Cepi class, there are many types of material which is called the electrode. For example, the classic carbon electrode and the CPE, gold, AG, PT, SPE, and so on. There are many types of transducer that you can use in here. And the next one, we need the analyzer. In here, the analyzer is, for example, the voltammetry, amperometry, potentiometry, this type of technique we can use in electrochemical analysis. And after this, we can see the signal using in display, right, as a signal processing. So this is the general concept of electrochemical sensor. What we are doing in here, what I'm doing in here is about this. So we are fabricating, we are engineer, we are studying this kind of transducer with the recognition that can specifically and selectively recognize our target analytes. Okay. So about the technique, for example, like voltammetry, amperometry, and so on, we also have a research about this, which technique actually is good for our sensor. So there are some types that we can use later in our devices. Okay, so I can summarize what we are doing, what I'm doing here with my group in Universitas Airlangga. So we are mainly working in electrochemistry area using several material, which is specifically on carbon-based material. For example, diamond material, glassy carbon, graphene, CNT, or carbon nanotubes, and many more. But mostly, Pak Cepi know that I graduate from K University under the supervision of Professor Yasuo Kainaga. So he is working a lot with diamond material. So I try to continue research in Indonesia, of course. So mostly our research in here is working on the diamond materials, especially for a biosensor or medical sensor, which we already tried for antibiotic sensor, artificial sweetener sensor, and also another pharmaceutical drug sensor. And also in environment, we also working on heavy metal sensor, for example, like antimony, lead, and so on. And this is our new work in here, which is for water treatment for pollutant degradations. So we are trying to degrade the dye, for example, like methylene blue, methyl orange, and so on. And the third one, we are working on the energy area for CO2 electrochemical reductions. We already write the review of our work in this book chapter. So if you have time, you can download and you can read this book chapter in collaborations with one of my colleagues from Faculty of Science and Technology who working on a nano diamond for drug delivery. Okay. So the first one, because we are working a lot on diamond material. So I'd like to introduce you in here because I believe that in Indonesia, not many researchers working on the diamond material. Especially maybe the first one is my supervisor, Professor Ivandini from Universitas Indonesia. There's me and my college in Unpad and Institute Teknologi Kalimantan also. I mean, not many. So only few researchers working on the diamond material in Indonesia currently. So I'd like to introduce this super material actually to you. So you can know that we can work many things with this material. So diamond, as you know, that the diamond is a very strong material, right? Has the largest most hardness, has the largest modulus, has a smallest thermal expansion coefficient, a very large refractive index, and a very large band gap. So by these all properties, it has a chemical inertness, which is very good. And the second one, it has a resistance to acid and alkaline and organic solvent. So if you use for example, like catalytic activity, it will be very nice. No problem if you use it in acid or very alkaline solutions or in organic solvent as well. It's no problem. It has very good stability. And the last is a non-toxic and biocompatible. So that's why one of my colleagues in here are working with the drug delivery using this diamond nanomaterial. So by these all properties, we always say that diamond is the king of materials, right? No wonder. Okay, so if we're talking about the nanomaterials, so we would like to combine the properties of nanoparticles and the properties of a diamond. In the properties of nanoparticles, we know it's a nano size. Nano size has a very large surface area, and it has a high absorption capacity, and also it's a biocompatible. And we have the properties of diamond here, which is a high Young's modulus, fluorescence, and also a chemical inert core. By these two properties, we can get a very unique nano diamond. Okay. And because we're working in the electrochemistry area, it's impossible to use only a diamond material. Because as you know, the diamond is insulator. Electrochemistry needs at least semiconductor or conductor. So it's impossible to use only diamond. So for this, we need to drop some material that can give a conductivity to materials, to the diamond itself. In these things, we can use the boron. So boron we are dropping inside the structure of diamond, and it can give the conductivity. So I don't have the CVD in here. So MPS CVD I don't have in here. So I always have collaborations with my supervisor, my previous supervisor, Professor Einaga. So he has this machine, the microwave plasma acid chemical vapor depositions, which is we can synthesize a boron diamond in here. But for example, you don't have the collaborations with anyone who can synthesize this, you can buy. So it's no problem. It's just like you can buy, like you buy a graphene, a CNT, and other carbon-based material. So there are many companies now sell this material. If you see in here, the morphology and topography of the polycrystalline BDD film, it's a polycrystalline, right? A diamond, as you see in here, and we can use this for electrochemistry. And what is special of the BDD beside another material? For example, electrode graphene oxide, CNT, and so on, or metal electrode, for example. So there's a distinct properties in here. It has a wide potential window. A wide potential window means you have a very large potential. Very large potential, right? Very large potential, it means you can analyze many things, larger than glassy carbon, gold, platinum, okay, and another material. And the second one, it has a low background current. A low background current means the distance between the oxidations and also the reduction is very small. So for example, you want to analyze a very small concentration of material. In the glassy carbon, for example, it's a little bit large, right? So if the sample is inside this background, then you cannot analyze that analyte. But if you analyze in boron diamond, because it's a very, very low background, then you can analyze a very small analytes in your sample. Okay, and the last one is has a high chemical and physical stability. No wonder. So for the real applications, we can apply this diamond. Okay, but now the problem is if we want to develop a sensor, it's almost impossible we use this large material. So this diameter, if we synthesize in CPD, the diameter is about 5 centimeter. Okay, so you can imagine it's a big material, right? It's a big material. So it's impossible for us to use this for sensor, especially if uses for a portable sensor and very small sensor devices, it's impossible. So for this, we need to synthesize a nano size material, right? So we have in here, we can synthesize using CVD, a BDD powder or a boron diamond powder or nanoparticles, which has a nano size in here. So by this powder, we can make such kind of a tint or ink, right? We can make an ink and we can screen print, or we can just like a home printing, we can do that. We can print as this kind of materials. So this is a very small. If you know the glucose sensor, you can now maybe searching in e-commerce, a glucose sensor device, for example, like that. Then you can get a very small device that usually used by the doctor or the hospital, or yeah, anyone can use that now. And you can buy by yourself, I think. So that kind of device, it's called a screen printed electrode. So we can make this kind of screen printed electrode using a BDD powder. So for this, we can make a very sensitive electrochemical devices. Okay, so it has possible for making composite material, large surface area, and applicable for printed material. Okay, so from this large material, we can have a very small device for sensing applications. Okay, so the first one, as I talked before, that we are working in antibiotic sensor. So why the first research that I do in Erlangga is about antibiotic sensor. At the time, if you remember, in 2020, that's the first time COVID-19 happened in the world, right? So in Europe, most of the hospital will give the antibiotics because they think that it's because of bacteria, not virus at that time. So it means that the antibiotic usage is very high, right? So if it's very high, then the people become resistant. That's the first one. And the second, it can be a pollutant in environment. So that's why I'm thinking of why not we making a antibiotic sensor. So this will be that would be our first research in Erlangga at that time in 2020. Okay, so I choose this type of antibiotic. The first one is levofloxacin, ofloxacin, ciprofloxacin, and azithromycin. Azithromycin used a lot for COVID-19 patients at that time. Levofloxacin, ofloxacin, and ciprofloxacin usually used in human and food-producing animal. So now if you eat, for example, like chicken, if you eat like beef, you may think about this because the farmers will give the antibiotics to boost their health, to boost or to prevent infection in animals. And if it's used in animals, if it's used a lot, right, it may uh, become the residue in the food, like in animal, uh, in food producing animal, like eggs or milk, or even the beef and the chicken itself. Okay, so if you consume a lot, in the long term, it may cause the heart problem, abdominal discomfort, and a rupture and bacterial resistance. That's the words, right? So to prevent that, we would like to know the concentration of antibiotic in the food that we always consume every day. Okay, the target at the time is this is what we would like to make. Like we make a very sensor devices like the glucose sensor that already sell and in e-commerce. Then I'm thinking to make that kind of device, but this is for antibiotic sensor, and we can analyze in our phone, so it's portable. You can analyze at home. You can analyze at school, anywhere, right? So at the time I study about this and we summarize in a review paper. So if you have time, you can read this review paper as well. Okay, so the first one, what we are doing, we are not going to the nanoparticles, the diamond nanoparticles, not yet. So we are working with the polycrystalline bond of diamond first. So in a burned up diamond electrode polycrystalline, we decorated or we modified the surface of the PDD using the nickel nanoparticles. So this is the SEM image of the PDD modified with nickel particles. So the white dot is the nickel nanoparticles deposited on the surface of the PDD. And we can use this using LSV and SVV. What is this? This is a linear sweep voltammetry, and SPV is a square wave voltammetry. SPV is more sensitive than LSV method. Okay, if you study electrochemistry, you can understand about this, right? So the square wave voltammetry is more sensitive than LSV. So in here, we can get the higher signal compared to the LSV method. Okay, so that's great. We can analyze antibiotic using electrochemical technique, especially using the boron diamond electrode. Okay, so we analyze the influence of the scan rate. That's a method, right? The method to optimize the electrochemical analysis. And we try also in various concentration, and we can get the linear correlation between concentration and the current. And we can get the limit of detection is about 11 micromolar. It's pretty small for analyzing antibiotic in foods or in environment. Okay, because we would like to analyze in human fluids, for example, like urea in urine, for example, or in blood. So we analyze the selectivity using urea, glucose, and ascorbic acid, because when someone usually consume antibiotic, usually they consume the vitamin, right? Vitamin C, which is ascorbic acid. So we try the selectivity using ascorbic acid. And the last, we analyze in urine sample, and we can get the signal clearly in the urine sample, and can get the selective sensor. Okay, so as I told before, I tried several sample, and this is the second one. We analyzed with using ofloxacin. Okay, ofloxacin. And we analyze using the burned-up diamond polycrystalline incomparable using the zinc nanoparticle decorated on the surface of the PDD. Why we use a nanoparticle? Because if it's only BDD, our target in the future is we use the BDD powder, so not only a polycrystalline. So we would like to try to make a composite with metal nanoparticles because it may give the more sensitive and a higher current usually using the metal nanoparticles. So we choose zinc in here, and it may give a higher signal actually using a zinc nanoparticle modified on the surface of the BDD electrode. And we compare this BDD and zinc BDD, and from this result, we can get the higher or the better result with zinc burned up diamond. Okay. And the next is because we already try using the polycrystalline burned up diamond, which is the big one. So we try using the burned up nano powder. So in here, I fabricate the burned up nano powder as a screen printed electrode, as may seen here. So I modified the working electrode with the burned up nano powder. But now in our lab, we are trying to screen print. So directly screen print the burned up nano powder onto the surface of the substrate, which is the mica or any polymer substrate. We can use that. So we try to produce ourselves this screen printed electrode. At the first try, we compare with the SPE. SPE means the screen printed, a commercial screen printed electrode, which is a carbon-based electrode in here. And we compare with our electrode that already modified with BDD nanoparticles, and we can get the higher signal on SPE BDD nanoparticles. As you may see, we already confirmed the characteristic of our electrode using SKM, XRD, UV, and as well as FTIR. So we can conclude in here that the BDD nanoparticle successfully modified on the surface of the screen printed carbon electrode. And it has a response for level focusing. So this is a good start actually for our research. And we try also to check the sensitivity and also the limit of detection. And it almost twice better than the screen printed commercial electrode. And we analyze as well in the real sample, which is in tablets, in milk, and also in wastewater. And we can get the good recovery in here. Cool. Okay, so we can conclude that we can analyze the residue of antibiotic in your food and milk or in environment which is in wastewater. Okay. And as you may know that the boron drop inside the structure of diamond, there is a specific concentration that we use. So it means that a lot of boron inside the structure means give a higher conductivity, right? So the conductivity of the electrode depends of how much boron we drop inside the structure, okay? So from this, we would like to optimize which boron concentration is best for sensor application. So we try to drop 0.1% boron. The second is 0.5% boron, and the last is 1% boron. In here, we can get the result that the best boron drop inside the structure of a diamond is 1%. We can get the higher sensitivity and the lower limit of detection. So for the next study, using the polycrystalline boron diamond, we use the 1% BDD. Okay. Okay. The last antibiotic we try is azithromycin. So azithromycin is effective in treating bacteria infections in various organs, body parts, such as the respiratory tracts, eyes, skins, and genitals. So in here, we try to modify the surface of the boron diamond using another carbon-based materials. We use the reduced graphene oxide because it contains residual oxygens, other heteroatoms, as well as structure defects. So these defects, this residual oxygen may give a higher electrical conductivity on the surface of the PDD. So we modify the graphene or reduce graphene oxide on the surface of the PDD electrodes. Okay, and in here we can get again the low limit of detection using our electrode compared to the previous result. Okay, we can get also the linear correlation between the concentrations of azithromycins and the current as well. And so in here, the reduced graphene oxide PDDNP screen printed electrode was successfully applied in real sample analysis using wastewater in hospital area. Okay, with a very good recovery. Okay, so another topic. Oh, no, not yet. So we also, I'm sorry, we also analyze here a ciprofloxacin. So we already working with the levofloxacin, ciprofloxacin, ofloxacin, and azithromycin. Okay, so we use another type of electrode because we are also interested with the reduced graphene oxide. So we try to modify the reduced graphene oxide with the thin nanocomposite. So we make a nanocomposite of RgOS and O2, and we try for the ciprofloxacin analysis. So in here, we can synthesize a very, very small size of thin, which is about 3.3 nanometers. You can see in here, this is the TEM image of SNO2 particles, and we make another composite with RGO. So we already confirm the characterization using SEM and as well as the XPS. Okay, so this work actually collaborations with one of my colleagues in Kyushu University in Japan. Okay, so for ciprofloxacin, we analyze also in canned milk, and also for environment application, we use the river water. And we can analyze clearly the ciprofloxacin inside the milk and also a river water in here. Okay, so this is a quite new research result in our group, which is the collaborations between us and with ITB. We use the detection of levofloxacin using the electrode of MAXIN. It's a quite new material, 2D material, which make a layer by layer like this. We would like to use this as a sensor. We modified this with the boron nanoparticle actually, and we use this for the sensor, and we can get here the higher sensitivity. Actually, a signal per background is higher compared to the use of BDD only. Okay, for this, can get a lower limit of detection compared to the previous result as well, about 0.39 micromolar. So from this, we already try several methods, or not several methods, but several electrodes we try for analyzing the antibiotics. And all of them actually show the good limit of detections. So hopefully after this, our target is we would like to screen print directly, so we make our own device. Usually we buy the screen printed carbon electrode and we modify as needed. But currently we are developing our own devices, which is our own screen printed diamond electrode, and we tried this for antibiotic sensor. So currently under developing. And the second one is our collaboration with the Faculty of Pharmacy and Queen University Belfast. So actually they have a microneedles. So our target, we would like to analyze the theophylline as an alkaloid compound that has a very narrow therapeutic window. Therapeutic window means if you consume this drug a lot or outside this therapeutic window, it may become toxic. And if less than that, it doesn't have a effect, actually something like that. So it means that we need the online monitoring of a theophylline used by the people who have asthma, right? So theophylline is the asthma drug. So we analyze this, we develop the sensor, and our first publications actually we are using the boron diamond modified vanillin nickel particles can analyze the theophylline in the low detection limit. As well as our new review, you can read that later. And this is our first publications on this development of the theophylline electrochemical sensor using BDD. So it shows in here, as you can see in here, it can get a higher sensitivity using nickel nanoparticle PDD. And currently we are working with this development. We combine with the microneedles and we directly attach to the skin, and hopefully that we can analyze the theophylline online. So the microneedle can absorb the interstitial of something like not a blood but similar, like it contains a similar materials with the blood inside under our skin, and using microneedles, and we attach our devices to the microneedles, and we can analyze the theophylline online directly when someone consumes the theophylline. So now I just saw in here because currently we are working in vitro study for that. But for the optimizations of the electrode, we can I can show you in here that it may be possible to analyze the turbulence itself. Okay, so the next for environment application, we analyze for the first time antimony electrochemical sensor using the boron doped nanopowder. Okay, so antimony, as you know, is one of the most commonly used metallic element in global reserve, about 1.9 million tons. Antimony is a catalyst in plastic production. So I think the second one is the one that you may need to be noticed, because it used as a catalyst in plastic productions. It means that the mineral water that you consume, if it under the sun, or if the temperature in the storage is a little bit high, then this tin may leach into your water. So we already have this experimental. So we put the water bottle, the commercial water bottle, under the sun for 5 days. Okay, so for 5 days, and we analyze the antimony inside the water itself, and it contains antimony. Okay, so only 5 days. So you can imagine if we drink the water that we buy from the shop that maybe expose this bottle under the sun, yeah, directly several days, then you consume antimony, right? So it's very dangerous actually. Okay, so we try to develop the sensor using boron doped nanopowder based current electrode. We use the buffer acetate as an electrode in here because it may stabilize the sp3 plus ions in here. And using this kind of electrode, we can get the signal of antimony. Okay. Okay, so if we compare with the previous study, it's quite low, the limit of detection. So we can analyze that very small concentration of antimony in water. Okay, and we try to analyze using several selectivity or compare with other metal ion, for example, this cobalt using ferrum and also lead, but we still can get the signal of antimony very clearly. So it's no problem. For example, if we want to analyze the antimony in river water, which is in the river, it may contain many types of metal ions, especially in Surabaya. You know, I don't know in your place, but in Surabaya, the river water is very, I can say, dirty. Sometimes the color is like a little bit black. So we take the sample from that river and we analyze in our lab, and we can find many types of metal ions actually in the river. So it is quite dangerous, right? So we try to analyze this antimony in that sample, and we can find the antimony inside the sample. Okay, so currently we are developing this sensor also to analyze precisely the antimony concentration in the water bottle or in mineral water that we always buy at the shop, right? Okay. And the next one, we also, okay, in the next time, we also analyze the artificial sweetener in the drinking water, for example, in soft drink, we are using this boron doped nanoparticles. So we modify the boron doped nano diamond using the zinc oxide nanoparticles. So we set up the experimental like this. This is for a big size of electrode actually, but we already changed the system now to be a screen printed electrode, so it can directly analyze or connect it with the potentiostat. So we don't use this type of a cell anymore for now. But our study several years ago, we used this with this kind of a cell, electrochemical cell, and we modify the electrode using the zinc oxide and the PDD nanoparticle. For this, we can analyze the aspartame, so the artificial sweetener in soft drink. We compare this sample, I think you already know, and we can analyze this aspartame in this sample very clearly, very precise, with a good recovery. Okay. So we compare our study also with the previous study, and we can get the lower limit of detection actually compared to the previous published study. Okay, sure. Our future directions actually in sensor application, still we are struggling to connect our device with our own application in our phone. Currently, we are still using the commercial applications, so developed already by this company, the Potentiostat company. But hopefully in the near future, we can connect this with our own application. So with a very a simple method, because now if we use the application or the software from the company, that the system is very complicated. So no one will understand. Only ultra-chemist people will understand. But our target is we would like to develop our own software so everyone can read. Like if we buy the glucose sensor in e-commerce, then we can read at home. So your dad, your mom will understand that. So that's our future direction. So we would like to make this kind of concept, sensor concept, and for analysis, medical sensor, pharmaceutical drug sensor, and as well as in environment. Because as you may know, maybe Erlangga University is very famous for its medical school as well as pharmaceutical school as well. So most of our research actually, even though we are in a department of engineering and we are focusing on nanomaterials, but we try to focusing our work for medical applications. Okay, so that's all. I'd like to thank you also for my team in here as a nanoelectrochemistry team, as well as the Erlangga Functional Nanomaterial Research Group and all the collaborators. I hope for next UNES will be in here. Hope so.
Okay.
Okay, that's all. Thank you very much, Pak Cepi.
Thank you very much, Bu Prastika. Wow, that's a lot of work. And congratulations for all those of the works. Okay,
you.
I would like to invite the participant probably have some question to be proposed or to be discussed to with Dr. Prastika. Bisa dalam bahasa Indonesia atau bahasa Inggris? Boleh, silakan.
Boleh,
I
silakan.
also would like to welcome Dr. Suni from Sogang University, and also previously I see Prof. Asep from UPI. Thank you for joining with this lecture, Dr. Suni. Silakan. Ada yang mau ditanyakan? Kalau belum ada mungkin karena tadi ada yang bertanya, ada yang meminta in bahasa please katanya. So
Oke, boleh,
Dr.
boleh,
Suni,
tidak
so
masalah.
I would like to discuss with the presenter in bahasa and also with the participant. Bu Prastika,
Ya.
saya ini tadi yang tertarik itu terkait dengan cemaran SB ya, antimoni dalam air yang salah satunya ternyata dari proses pembuatan ini ya, kemasan gitu ya.
Betul.
Nah, uh, di situ ada sebarannya sampai ke liver dan ada tikus gitu. Nah, kemudian di penelitiannya Bu Kristika tadi sepertinya ada yang menarik yang ingin saya tanyakan, bisa ke slide setelahnya Bu. Before maybe. Uh, Next before.
This
Nah,
one.
nah
Ya.
di sini. Uh, I wondering the use of
What's this?
buffer asetat dalam
Ah, oke.
dalam dalam deteksi antimoni ini.
Mm-mm. Mm-mm. Oke.
Kenapa menggunakan buffer asetat ya Bu?
Betul, betul. Jadi buffer kita kemarin itu sudah mencoba menggunakan beberapa buffer sebenarnya. Namun yang paling pas dan memunculkan signal yang terbaik itu di buffer asetat. Nah, ternyata setelah kita
Hmm.
research ya, kenapa it become the best signal actually in acetate buffer karena dia bisa menstabilasi ternyata, stabilisasi
Oh,
ion dari ion antimoni tersebut seperti itu. Jadi ketika kita melakukan stripping eh, signalnya itu bisa bagus gitu. Ada
I
beberapa
see.
yang buffer yang lain yang kita pakai ternyata signalnya itu kecil. Ada sebagian yang tidak
Oke.
terdeteksi seperti itu.
Oke,
Ya.
berarti uh, dalam dalam analisis spektrometri itu apa elektrolit, buffer sistem itu juga sangat mempengaruhi ya dalam
Betul. Betul sekali Pak Cepi.
deteksi
Jadi
ya.
betul, ketika kita memiliki analit, misalkan seperti analit obat-obatan, seringkali kita pakai buffer PBS, ya salin, karena memang
PBS ya,
memang
common one.
pas gitu ya, kan well.
Ah,
Jadi yang digunakan itu. Namun untuk logam-logam itu terkadang menyesuaikan gitu ternyata ya.
hmm,
Kita ada salah satu research yang mungkin tidak belum saya tampilkan di sini ya, yaitu cemaran 3 mcpd di minyak. Ya. Nah, 3 mcpd, nah kita coba di beberapa buffer seperti PBS dan lain-lain yang biasa kita gunakan, itu ternyata nggak bisa, Pak, gitu. Jadi pas waktu
ah,
kita searching, "Ah, kenapa ya gitu, ternyata dia larut di dalam NaOH, ya kan, dalam
I
basa. Oke,
see.
akhirnya kami menggunakan basa dan bagus gitu hasilnya. Jadi memang ketika menentukan elektrolit ya, mungkin ada mahasiswa nanti yang melakukan penelitian akhir ya,
Hmm,
dilihat dulu analitnya gitu. Jadi
I
analitnya
see.
apa, kemudian nanti kita harus searching ya mungkin dari riset-riset terdahulu, dia biasanya
Hmm,
larutnya di mana gitu ya. Tidak semua analit itu larut di dalam BPS gitu. Ada beberapa yang larut mungkin di dalam basa, di dalam asam gitu. Dan kondisi eh, apply apa namanya elektrokimianya juga harus disesuaikan dengan elektrolit yang sesuai dengan analitnya untuk bisa
Oke.
mendapatkan hasil signal yang maksimal. Biasanya mahasiswa kok tidak ada ya Bu ya signalnya gitu. Nah, coba dulu elektrolitnya
Betul,
apa.
betul.
Ya, ternyata belum sesuai. Nah, ketika diganti hanya diganti elektrolit saja sudah bisa gitu. Jadi
I
itu
see.
harus
Oke,
diperhatikan ya.
tips yang menarik ini. Terima kasih. Silahkan, barangkali sudah ada yang punya pertanyaan.
Silakan ya, maksudnya secara general nanomaterial atau elektrokimia sendiri.
Nah, boleh tuh katanya sudah di open untuk nanomaterial secara umum juga boleh. Yang tertarik
Iya,
dengan metode sintesis tadi BDD,
oke. Mohon maaf, saya pikir ini ya ternyata banyak pesertanya dari mahasiswa mungkin tadi bisa lebih general ya. Ini lebih mengarah ke riset.
it's okay. Yeah, just because the aim of this webinar actually to introduce the research trend. So
Nah,
uh,
oke.
saya pikir nanti bisa memacu mahasiswa untuk belajar lebih banyak terkait dengan riset-riset uh, yang lebih luas karena di kami khususnya kebanyakan riset itu kan sifatnya itu lebih banyak turun-temurun gitu. Jadi
Oh ya.
sometimes kita tidak melihat sebetulnya di dunia bagian lain itu penelitian kimia itu sudah sampai mana gitu. So
Hmm.
this is the aim of this activities. Uh, Jadi untuk introduce terutama kepada para mahasiswa, kira-kira nanti mau riset dengan kimia itu apa nih yang bisa menarik dan bisa dilakukan di kampus
Betul.
masing-masing, atau mungkin nanti bisa kolaborasi dengan Bu Tika di eh,
Very welcome.
Erlangga gitu.
Iya,
Oh, oke, Di,
monggo, silahkan. Ya.
you might raise the question directly, Di, atau mau saya bacakan saja. Oh, ini.
Mm-mm.
Adi Arya Kusuma dari Kimia UNNES Angkatan 21 ingin bertanya, saat ini sedang melakukan TA di BRIN dengan topik sintesis nanopartikel emas dengan bantuan polifenolpiridon untuk aplikasi sensor kolorimetri logam PB.
Mhm.
Tips untuk aplikasi sensornya waktu saat ini masih disintesis AU nanopartikel. Oh, oke. Jadi mungkin ada alternatif nggak untuk
Mhm.
analisis PB secara kolorimetri selain dengan AU nanopartikel? Mungkin gitu ya, Bu Tika.
Mm-mm. Iya. Baik, terima kasih ini Adi ya, angkatan 21. Oh, berarti lagi proposal ya, menuju skripsi.
Ya.
Iya. Oke, PBS ya, sintesis nanopartikel emas dengan bantuan PVP ya. Jadi PVP bisa menjadi capping agent gitu ya untuk menstabilkan nanopartikel emas. Jadi PVP biasa digunakan gitu ya untuk proses capping agent karena kalau misalkan hanya kita sintesis nanopartikel emas tanpa capping agent biasa beberapa hari itu sudah apa namanya menggumpal gitu. Jadi sudah nggak berbentuk nanopartikel. Jadi biasa digunakan PVP ya dan capping agent yang lainnya. Kemudian untuk aplikasi sensor kalorimetri logam berat pipi, apakah ada tips untuk aplikasi sensornya? Tipsnya sudah dicobakah untuk aplikasi sensornya? Karena kalau sensor itu em, apa ya? Utamanya logam ya. Jadi logam yang banyak dipakai, misalkan saja emas. Emas itu akan banyak dipakai untuk sensor-sensor yang hubungannya mengarah ke biosensor, gitu. Karena dia
Hmm,
akan sangat
betul,
mengikat komponen biologis dengan sangat stabil dibandingkan
betul.
logam lain. Nah, jikalau memang menurut saya ya, jika tidak terlalu ke biosensor, sebenarnya bisa memilih logam-logam yang lebih relatif murah mungkin ya harganya selain
Hmm,
AU. Meskipun memang AU the best lah, maksudnya kalau untuk sensor ya di kalangan logam. Nah itu sebenarnya bisa mencoba misalkan AG, NI ya. Saya banyak pakai NI karena dia relatif murah dan tidak ada peak redox berarti yang akan mengganggu pengukuran. Ya, berbeda misalkan kita menggunakan CU. Nah, CU itu redoxnya sangat sempit sehingga jika kita gunakan untuk sensor, biasa dia akan berpengaruh karena signal sensor kita atau signal analitnya itu bertabrakan dengan redoxnya CU.
betul.
Nah, itu bermasalah gitu. Jadi, pemilihan logam bisa mempertimbangkan itu, seperti itu.
Oke.
Oh, ini masih di sintesa. Jadi, ini sudah berhasil ya sepertinya di sintesan. Ada mahasiswa S3 di sini, di bawah bimbingan saya juga, itu sedang pakai metode ini gitu untuk sintesa AO
Oh,
dan bisa bertahan berapa bulan ya, sampai kita cek kemarin stabilitas 3 bulan masih oke gitu
oh
ya.
sih, menarik.
Jadi bagus saya rasa dengan metode ini, tinggal nanti untuk sensornya ya dicoba dulu gitu ya untuk
Hmm,
kolorimetrinya. Kalau
oke.
kolorimetri biasanya less sensitif ya dibandingkan dengan electrochemical. Tapi untuk apa namanya analisis yang
Rapid
cepat
ya.
gitu kan,
Hmm,
rapid itu bagus sih. Bisa
ya.
dicoba.
Begitu
Kira-kira
Adi.
demikian.
Silahkan boleh langsung diskusi saja.
Ini malu-malu kayaknya Pak ya.
Heeh. Kalau tidak,
Silakan.
ini saya punya ini, punya mahasiswa yang juga sedang melakukan penelitian analisis PB, Bu Tika. Uh,
Baik.
we are trying to modify the SPCE
Mm-mm.
with the organic compound.
Oke.
Yang sebetulnya kami beranggapan bahwa yang kami sintesis ini adalah suatu ligan yang
Mm.
kalau misalnya dia diinteraksikan dengan logam akan membentuk senyawa kompleks sehingga mudah gitu pendeteksiannya. But in
Oke.
fact, eh, setelah kami imobilisasi di SPCE, sinyal dari heavy metals itu tetap tidak terdeteksi. Malah sebelum
Oke.
dimodifiednya itu ada
Mm-mm.
ada sinyalnya gitu.
Mm-mm.
Any tips maybe?
kenapa gitu ya Pak?
Mm,
Pasti ini ada diaktifasi, saya yakin. Jadi eh, ada juga beberapa yang kasus kayak gitu. Jadi kita pakai binder. Jadi waktu sintesa sendiri, jadi kita fabrikasi screen printing sendiri memang.
mm.
Nah itu kan pakai binder, di mana bindernya itu insulator gitu ya.
Ah,
Sehingga ketika kita gabungkan dengan logam nanopartikel juga kita buat nanokomposit. Nah, ternyata
mm.
posisi bindernya itu justru
Lebih
di
dominan.
atas
Oh, di atas.
menutupi dari
Ah,
logam nanopartikel yang kita pakai. Sehingga signalnya justru turun. Kita lihatnya dari bukan ada atau tidaknya ya. Kalau ada atau tidak
mm,
itu kadang bisa dioptimasi misalkan dengan SVV atau DPV. Tapi kita lihat dari eh, resistivitas itu yang menggunakan
mm.
impedance gitu ya. Nah, dari impedance ternyata
Ah,
kelihatan gitu resistensinya itu jauh lebih tinggi ketika
I
dimodifikasikan dari yang
see.
sebelum SPCE yang komersil gitu. Jadi yang perlu diperhatikan lagi tadi membuat ligannya tadi ya kompleks ligannya itu seperti apa gitu. Apakah sudah benar atau mungkin belum atau memang ketika di dropcast ya Pak ya ininya ya modifikasinya.
Dropcast.
Ketika di dropcast justru logamnya itu di bawah gitu tertutup ya sehingga dia sisi aktif
Oke.
dari SPCE-nya justru yang tertutup seperti itu. Kemungkinan besar terjadi seperti itu. Dan kalau sudah seperti itu mau diaktifasi dengan CV misalnya scanning berkali-kali tetap tidak
Mm.
bisa.
I see.
Tapi bisa dicoba dulu mungkin dengan scanning ya, diaktifasi dengan scanning
Oke.
CV dari
Mm-mm.
potensial mungkin -1 berkali-kali 40 kali cycle mungkin ya. Kalau
Mm-mm.
tetap tidak berhasil ya mungkin tadi itu. Jadi karena materialnya sendiri gitu yang nggak bisa.
Oke.
Gitu.
Begitu Ican. Nah, silakan mahasiswa yang penelitiannya
Oh iya.
gambate di lab. Oke, there is another
Iya.
question. Zola. Zola pakai voice aja tuh.
Iya.
Bisa,
Hmm,
Zol?
biar ada suara yang lain nih. Nggak saya dengan
Heeh.
Pak Cepi saja ya. Malu.
Semester 4 sangat tertarik dengan biosensor
Oke.
untuk mendeteksi molekul glukosa dalam tubuh manusia menggunakan
Mm,
sampel air liur manusia. Namun untuk
mm.
biosensornya menggunakan fotoelektroda dari kaca induktif ITO dan FTO yang dimodifikasi dengan oksida nanokomposit ZNO SiO2. Ah, namun saya di sini juga hanya membandingkan kinerja sensitivitas biosensor fotoelektroda ITO dan FTO yang dimodifikasi. Apakah penelitian biosensor tersebut kini akan bekerja dengan baik?
Wah, baik. Oke, terima kasih pertanyaannya. Sulit ini dijawab ya. Apakah penelitiannya pada biosensor tersebut sekiranya akan bekerja dengan baik? Karena kalau tidak dicoba, kita tidak tahu, gitu
Mhm,
ya.
betul.
Jadi eh, kalau terkait dengan ITO dan FTO, saya rasa karena dia sebagai substrat, ya substrat ya, kaca
Mhm,
induktifnya saya rasa tidak masalah. Yang menjadi masalah nanti sebenarnya nanokompositnya ini ya ZNO
mhm,
dan SiO2. Nah, ini band gap-nya harus disesuaikan dengan redoksnya dari glukosa. Itu apakah sesuai atau tidak? Karena kalau misalkan fotoelektroda atau fotoelektrochemistry itu
mhm.
ada berbeda dengan elektrochemistry biasa. Jadi materialnya ini band gap-nya harus dihitung. Jadi yang masuk ke dalam band gap analit yang mau kita analisa gitu. Jadi contohnya sebagai contoh sekarang ada yang sedang bekerja juga, tapi bukan untuk sensor ya, tapi untuk fotoelektrokatalisis ya. Kebetulan memakai material BDD juga, tapi BDD itu kan band gapnya terlalu lebar ya, sehingga tidak
Ya.
masuk untuk aplikasi yang kami sedang pakai itu adalah aplikasi reduksi elektrokimia CO2. Nah, itu
Mhm,
tidak
mhm.
masuk. Akhirnya kita mencari yang band gapnya bisa masuk ke potensial reduksi CO2. Nah, jadi di situ kita modifikasi dengan MOF dan salah satu saya lupa namanya GCN ya, salah satu jenis material singkatannya GCN gitu kan. Graphite nitrate something gitu ya, saya lupa
Mhm,
namanya,
mhm,
nama
mhm.
kepanjangannya. Nah, kita modifikasi dengan itu sehingga ketika dihitung ya, jadi kayak ada digambarkan gitu ya. Kemudian nanti band gapnya bisa masuk. Nah, itu bisa
Ah,
bagus hasilnya. Jadi untuk ini, untuk tahu optimal atau enggaknya, mungkin secara teoretikal bisa dihitung dari band gapnya. Dan yang kedua ya tetap harus dicoba sih. Seperti
iya.
itu.
Dan dengan
Kadang,
FTO
mm-mm.
itu ini ya Bu Tika, apa potensial Windows-nya
Mm-mm.
eh, agak
Agak
sempit
melebar ya,
ya,
Pak. Sempit ya malah ya, Pak. Iya,
betul.
dengan FTO. Gitu. Jadi nanti bisa dipertimbangkan untuk tapi ini
Mm-mm.
sensor ya. Foto elektroda of sensor. Oke.
Ya untuk elektroda
Em,
sensor
nah,
glukosa.
iya. Terus terang kalau misalkan foto elektroda untuk sensor, kayaknya belum pernah sih, karena kan ya sensor harus pakai cahaya, harus pakai listrik. Jadi ini juga gitu. Kebanyakan yang kami pakai untuk foto dengan foto elektroda itu dengan foto elektrokatalisis
Foto
memang karena kita
elektrolysis.
butuh untuk apa proses katalisisnya kan perlu ini ya Pak ya, apa namanya
Mm.
radikal bebas dan seterusnya. Jadi kebanyakan kita aplikasikan ke katalisis.
Oke,
Itu belum saya sampaikan sih di presentasi karena untuk sensor memang.
ya.
Jadi ya tadi di bagian CO2 reduksi kita ada mengerjakan untuk itu.
Oke, terima kasih jawabannya Bu Tika dan terima
Baik,
kasih
semoga
Zola.
menjawab. Thank
Semangat
you.
Zola. Oh, ini
Oke.
ada lagi.
Mm-mm.
Raihan, saya tertarik dengan topik sintesis hijau nanoperak. Yang saya ketahui, nanoperak ini merupakan material yang cukup mudah teragregasi, sehingga jika
Mm.
sudah selesai disintesis, sebaiknya segera dikarakterisasi di hari yang
Oh.
sama. Misalnya, salah satu, adakah perlakuan tertentu jika karakterisasi tidak bisa dilakukan di hari yang sama untuk menjaga kestabilan material yang disintesis?
Oke.
Silver
Em,
nanopartikel berarti ini.
ya, terima kasih Rehan. Jawabannya ada, tapi sulit, perlu bahan yang banyak. Kenapa demikian?
Hmm.
Karena Ag nanoperak itu hasil dari sintesis nanopartikel ini bisa sedikit sekali. Dan untuk
Hmm.
menjaga kestabilannya, misalkan untuk PSA, itu betul saya setuju harus dianalisa di hari yang sama. Jadi ketika hasil setelah direduksi itu ya, itu langsung dianalisa dengan PSA. Namun seperti case yang saya selalu hadapin gitu ya, tidak mungkin kan biasa untuk karakterisasi XPS, TEM gitu,
Ya.
saya lebih senang mengirim ke kolega yang di luar gitu daripada saya analisa di Indonesia gitu. Sehingga untuk mengirimkan sampel itu impossible dalam bentuk larutan gitu, riskan terjadi di jalan. Sehingga yang saya lakukan adalah membuat powder gitu. Jadi
Hmm.
kita keringkan gitu ya di centrifuge, terus kemudian di oven, jadi dikeringkan jadi powder. Jadi yang kita simpan adalah dalam bentuk powder. Nah itu bisa jauh lebih stabil dibandingkan dengan menggunakan koloidnya gitu. Tapi yang menjadi masalah adalah agen partikel biasanya kalau kita keringkan itu sangat sedikit sekali hasilnya
Hmm.
gitu. Tapi untuk analisa yang misalkan kayak FSM, TEM, XPS itu kan hanya sedikit saja, satu titik aja itu sudah bisa dianalisa. Jadi
Hmm.
no problem gitu, sebenarnya nggak masalah. Seperti itu. Mungkin itu tips yang sering kami lakukan seperti itu. Disimpan dalam bentuk powder gitu.
Ini kan kalau misalnya menggunakan bioreduktor ya, kalau misalnya menggunakan
Mm-mm.
chemical reduce gitu, tetap
Sama,
akan
Pak.
tidak stabil.
Sama, Pak. Sama. Tidak akan
Hmm.
stabil kecuali dikasih capping agent. Gitu.
Capping
Kalau
agent ya.
seperti tadi AU dengan PVA itu akan bisa bertahan
PVP ya.
lama.
Ya.
Jadi kita membandingkan PVP dan capping agent yang lainnya lah dengan yang tanpa capping agent. Nah, yang tanpa capping
Hmm.
agent itu di minggu berikutnya aja sudah aglomerasi. Dilihatnya
I
dari
see.
mana? Dari signal UV-nya. Jadi ketika kita bikin nanopartikel kan biasa kita
Geser
cek
ya.
dengan UV. Nah, itu sudah bergeser, artinya sudah
Hmm.
berubah. Nah, ketika pakai capping agent dia akan tetap di titik yang sama. Biasanya seperti
Hmm.
itu. Ya, jadi kalau chemical memang akan lebih baik dikasih capping agent gitu.
Hmm.
Atau kalau mau lama ya silakan dipowderkan gitu. Meskipun hasilnya biasa sedikit sekali
Hmm.
seperti
Hmm.
itu. Jadi memang harus hati-hati apa ya, taking care lah dengan sampelnya. Seperti
Oke.
itu.
Terima kasih. Itu ya Raihan ya. Jadi semangat mencari capping agent.
Iya.
Harus dioptimasi memang. Betul. Baik, mungkin saya satu lagi penasaran ini Bu Tika. Saya belum pernah
Oke.
sebetulnya
Mm-mm.
kalau tadi Bu Tika saya lihat ada analis apa sensing ada
Mm-mm. Yang
atau
set stop.
minuman.
Oh iya.
Ada treatment tertentu sebelum dianalisis dengan elektrometri seperti kalau misalnya kita AKS kan harus
Mm-mm. Mm-mm.
didestruksi dulu gitu.
Mm-mm.
Nah, untuk
Oh, ada.
untuk elektrometri ini apakah serumit itu juga atau bagaimana ya?
Tidak, Pak. Jadi untuk analisa, misalkan dengan minuman, elektrokimia itu kan basisnya kalau ada elektrolit ya bisa dianalisa gitu.
Mm-mm.
Atau misalkan minuman seperti ini kan ya dia bukan elektrolit gitu. Sehingga yang
Ya.
kita lakukan dilakukan pengenceran. Jadi mungkin diencerkan saja sampai relatif encer ya, entah 1:1, satu
Mhm,
banding
mhm.
tiga seperti itu. Kemudian sisanya ditambahkan elektrolit. Nah, itu sudah bisa terukur.
Oke.
Seperti itu.
Berarti
Jadi
memang metode
uh-uh,
elektrometri ini cukup sensitif
lebih simple dan sensitif.
dan betul ya. Jadi interferensi
Sebagai
dari lingkungannya nggak begitu ini ya. Maksudnya bukan dihindari, diminimalkan
diminimalkan,
dengan
dibedakan
dengan
gitu.
menggunakan apa potensial atau elektroda yang sensitif
Betul,
gitu ya.
betul. Mungkin sebagai
Oke.
notes kalau misalkan sampelnya bukan cair.
Hmm.
Karena kan elektrokimia bekerja ya di sampel yang aqueous atau organic solvent seperti itu yang
Mhm.
dia menghantarkan listrik kayak harus menghantarkan listrik itu syarat utamanya. Sehingga misalkan seperti sampel minyak, ya kan impossible gitu. Kita nggak bisa
Betul, betul.
kayak tadi kasusnya misalkan saya mau analisa cemaran 3 mcpd di minyak sawit itu kan itu nggak
Mhm.
mungkin karena sampelnya minyak. Sehingga yang
Ya,
dilakukan harus dilakukan ekstraksi kimia.
ekstraksi.
Gitu. Jadi diekstrak dulu, baru bisa dianalisa ditambahkan elektrolit. Jadi minyaknya dihilangkan, lemak-lemaknya.
Mhm.
Itu memang ada treat khusus untuk yang sampel-sampel seperti itu. Tapi kalau sampel perairan yang basisnya air ya langsung saja bisa. Gitu.
Oke. Menarik. Saya belum banyak mengeksplorasi karena saya juga kalau dulu di katalisis,
Mm-mm,
sekarang masuk ke sensor karena ada
mm,
kolaborasi juga dan kebetulan
mm,
saya baru baca proposal yang diusulkan PKR-nya Undip. Oh ternyata Butika
mm.
juga di situ gitu.
Iya, dipanggil Pak Marcel. Saya baru kenal juga dengan Pak Marcel di IBA ini, dihubungin terus oh
Sama
oke.
saya juga ini deket
Oh
Undip UNES
iya.
deket tapi belum pernah ketemu
Oh
juga.
gitu. Iya, iya. Gitu, Pak.
Baik, itu ya
Hmm.
teman-teman mahasiswa. Diskusi dan juga lecture dari
Baik.
Butika. Alhamdulillah kita sudah ada di ujung sesi. Thank you very much for your kind explanation, experience, and also excellent works sharing with us, Butika.
You're welcome.
Sukses untuk kedepannya.
Anytime. Ya. Terima
Mudah-mudahan kita
kasih, Pak
bisa
Cepi.
kolaborasi di kemudian hari.
Tentu
Dan
saja.
mudah-mudahan bagi teman-teman mahasiswa bisa membuka wawasan bahwa riset-riset dengan pendekatan elektrokimia itu sangat menyenangkan.
Betul.
Tentunya banyak
Terima kasih.
tantangan, tapi ya segala sesuatunya harus dicoba. Kuncinya itu tadi ya, harus dicoba.
Ya.
Kalau misalnya kita tidak mencoba, ya kita tidak akan tahu responnya seperti apa. Again, thank you very much for your attendance, Bu Tika,
Ya.
and also for the attendance of the participant from UPI, UNES, and also UNDIKSA, and so also from Sogang University. See you in the next webinar. Uh, we wish to conduct this activity monthly. If there's the speakers are ready, we are going to announce immediately to all of you. And if you have any suggestions, so you can fill the attendance list. And at the end, you might suggest to us who are the speaker that we can invite and the topic you are suggesting to be delivered. Um, that's it for today. Thank you, Butika, for your
Okay.
appreciation. I'd like to
My pleasure.
share this. So I will send this to you personally
Oh,
later by email.
okay.
Thank you
Thank
very
you
much.
very
This
much. Thank
certificate
you.
is to certify your lecture today. I
Thank you.
hope this is not the first. This is the first, but not the end of our lecture.
Of
So
course.
sometimes I can also invite you again
Sure.
to talk in other topic. Thank you very
Okay.
much.
My
And for
pleasure,
other
Pak Cepi.
participants, the uh, certificate will also sent by email once you fill up the attendance list. Okay, thank you very
Okay.
much. Thank you, Butika. See you
Terima
in the
kasih
next
banyak, Pak
webinar.
Cepi. Thank you for invitation. See you.
See you. Oke, silahkan bagi yang belum mengisi kehadiran bisa mengisi sampai dengan jam 3 hari ini. Saya tutup Zoom ini. Assalamualaikum warahmatullahi wabarakatuh.